and welcome to this section of the course. In this chapter, we'll be looking at composite functions. Composite functions are functions that involve more than one function, one side of one function applied after another function is applied to the input. For example, we have f of x to be x squared and g of x to be x plus 1. We've been told to calculate f of gx. That means g of x is applied first in the inputs, and then the output of g of x is applied and fed into f of x. So when they say find, what they mean is algebraic formula. So we're not calculating anything. So all we have to do is say whatever g of we need to square it. Okay, so the way to do it is just write x plus 1 inside the bracket and square it. What's the square of x plus 1? You can expand the bracket and you get x squared plus 2x plus 1. And asked to do it the other way around. G is the wrapper function. By wrapper, I don't mean wrappers who sing. I mean wrappers as in when you wrap a box of present for your family or friends. Okay, so wrapper function is on the outside. That means that x squared will be inside of g. So g is the definition of g is x plus 1, or the input plus 1. That simply means that x squared plus 1. So let's look at another function. In these two cases, in this example, we have f of x equals to 3x plus 2 and g of x is x squared plus 4. Going through the same motions, f of g of x means that g of x will be fed into f of x. That means that where we have an input for f of x, we leave an open bracket 3x plus 2, and we leave a gap for the input, and we are going to insert what g of x is to inside f of x. So what I'm figuring out is f of g of x. That means that I replace g of x with x squared plus 4, and I expand the bracket. Simply, that means 3x squared plus 12 plus 2, which is 14. So that's the definition of f of g of x. Now, in part B, we've been asked to calculate the functions other way around. G is on the outside, so where I have x squared plus 4, I open a bracket and I put the square on it and I write plus 4. This is g of f of x. So f of x have to go inside this bracket. That means 3x plus 2 needs to be squared before we add 4. That means that we will have 9x squared plus 12x plus 4 plus another 4. One of these 4's is from 2 squared, the other 4 is this 4 here. Therefore, we'll have 9x squared plus 12x plus 8. So we've done part A and B. Here, we've been asked to calculate f squared. This square means apply the function to itself. Don't confuse this with 3x plus 2 times another 3x. This does not mean to take 3x and just square it. That would be the wrong thing to do. This means that write 3, open a bracket, write 3, open a bracket, and write plus 2, and inside the bracket, write 3x plus 2 again. That's the meaning when you have functions like so. If they wanted you to do this, they would have put the bracket like so, and they would have put the square outside the function like so. They would have put the square on the outside. So this bracket is simply 9x plus 6 plus 2. is 9x plus 8. So this is a common mistake some students make. Make sure you avoid it. In part D, we've been asked to calculate the value of f the value of b when the output of function is 62. Where we have already calculated what f of g of x was. F of g of x in part A was this expression here. Let's use it here. So f of g of value b has to equal to 62. That means that 3x squared plus 14 has to equal 62. We subtract 62, we subtract 14 from 62, and we'll have 48. So 3x squared equals 48. Then we divide by 3, and we'll have x squared equals to 16. Then we're going to take the square root. Square root of 16 is plus or minus 4. Okay, let's look at another example together. In this third example, we've been given such functions. Notice f double dash double dot means the same thing. This is another notation that you should be familiar with. So when you see f double dot x, that means f of x equals to 2x minus 8. So don't be afraid of this notation here. This notation with the arrow is exactly the same as the line above. And of course, this is the same as g of x being equal to this fraction here. So the arrow is simply pointing to what the function definition is. In part A of this question, we've been asked to calculate f of g of 3. Let's look at what f of x is and what g inside of f of x will look like. That means putting this fraction x plus 1 over 2 inside of f of 2x minus 8 inside the modulus. So that's what the meaning of f of g of x is. Let's simplify it. Expanding the bracket here will cancel away the 2's, and we are left with simply x plus 1 minus 8, which is x minus 7 inside the modulus function. So what we are asked to do is just substitute 3 for x. That's what we can do. 3 minus 7 is minus 4. But modulus function tells us to take the positive value. I'll show you another way you could have done it. You could have simply put 3 inside of g first. You could have evaluated this expression 3 plus 1 over 2, which is a 2. Then the output of this function goes in for the input of the f function. What we would get is 2 times 2 minus 8, and then take the modulus of minus 4. You'll end up with the same answer. So we've answered part A. Let's look at part B. Part B is f of g of x equals to x. We've been asked to solve this equation. Well, we would have needed to write that equation first. Luckily, we've already written the simplified version of f of g already. F of g of x was this line here. So we are simply going to take that line and equate it to x. That means solving this equation here. First, I'll look at the negative version of the modulus function. Expand the bracket and add the x to both sides. We'll end up with 2x equals to 7, and we divide by 2. Okay, that's one answer. Do I need to bother with the positive version of the graph? If you think about it, I'll show you that you don't need to. Because here, we'll end up with, if we take the positive version here, and say x minus 7 is equals to x, there is no solution to this equation, because we'll have to subtract x from both sides. And in fact, this equation doesn't even make sense. Why doesn't it make sense? Let's look at the graph for these two lines, where we will have this modulus function and y equals to x. I'll show you that on the next slide. We went through the working out and we calculated that f of g of x was so, and let's plot the graph here. We'll have the graph of the modulus function, and f of the other side of this equation is x. So that means y equals to x. Notice there is only one intersection point, because the gradient of this line is the same gradient as x plus minus 7. X minus 7 has the same gradient as x. Therefore, they don't intersect at all. Therefore, this equation doesn't make sense and doesn't have any solutions. Okay, so with that done, let's look at the part C. Part C of this question is not in your book, but I've made it up just to give you a good taste of what exam questions look like. Okay, part C actually has an extension as well, but let's look at part C, part 1. Let's read it and understand it. The question says, state the range of values of k such that this expression, which we evaluated to be x minus 7 inside the modular sign, is equals to kx plus 4. Kx plus 4 is a linear line, but we don't know what the gradient is. Let's plot the graph and make some sense of what it means. The modulus function we already know looks like so. We are sure that the intercept of this line is 4, positive 4. Therefore, we can draw a line like so. We are given this linear line in an abstract form, where this value for k is unknown, and we are asked to say what range of values it could take, so that we will have two solutions to this equation. Solutions means two intersection points. Well, at this point, if the graph is intersecting only once, we can say what the gradient is. And we know that if we rotate the blue line anticlockwise, we will get two solutions, okay, to 2, as long as the gradient is higher than what it is already. What is the gradient here? We'll have value of 4 for the intercept here, blue line, and the change in x is 7. So we have a negative change of y of 4, and we have a 7 for the denominator. Now, what we are saying is that as long as k is larger than this value of negative 4 over 7, we will have two intersection points. But do we? What if the graph, the blue line, let me draw it in blue, blue line rotated from this point all the way to the point where its gradient is 1. So from the previous working out we looked at, we know that once the gradient turns into 1 or higher than 1, so that's rotating anticlockwise further above 1, it wouldn't have any, it would only have one intersection point, and it wouldn't meet this line here again. So value of k has to be bounded between minus 4 over 7 and positive. It has to be less than 1, so that it will intersect the curve, intersect the red line twice. So answer to this part is k has to be, let's write the inequality signs the other way around. So k has to be bigger than minus 4 over 7 and strictly less than 1. Okay, so that answers this part of the problem. At least two solutions. Let's read the next example, next part. Now, to state the range of value for k such that that linear line, the blue line, will have only one solution with, or rather have only one intersection point with the red line. That means that the gradient and that the blue line will only have to meet this curve here. The the blue line kx plus 4 will have to equal to only negative x plus 7. Okay, so let's explore that. And if you're not sure and you find this rather abstract, you can plot these with Desmos calculator. But I'm going to do it just for the hand. We already figured out once the gradient is bigger than 1, that is k, the value of k is 1 or more, we will have only one intersection point. And we can keep rotating this curve until this point here will come down here. Once this line turns into parallel to this part of the graph, then we will stop having any intersection. So at what point will we have a parallel line between parallel lines here and here? Well, what's the gradient of this line? The gradient is -1. If the gradient, if Rk that once turns to +1, actually is bigger than 1, is it will have only one intersection, and when k turns to be less than -1, it will turn to have. So if you have trouble imagining this, just put your pencil on your paper and start rotating your pencil. Any value where value of gradient of the blue line is larger than 1, and once we start rotating any value of the gradient up to infinity, that means there is no upper bound that will give us at least one intersection point. But what if when we have the line going to the left, that means here or here or here, that means the gradient turns negative. It can be negative as well. So we have to write our answer as two disjoint sets. It can be bigger than 1 or it can be negative. How can it be negative? It could be from negative infinity up to a certain value. What's that value? That value is when the graph turns exactly parallel to the negative gradient of -x minus 7 plus 7. So once the gradient is less than -1, actually will stop intersecting completely. Therefore, the other answer is when k is less than 1. Okay, so for us to see only one intersection point, k has to be strictly larger than 1 or strictly less than -1. This is the answer to this part of the question. Okay, if you have trouble imagining this, I'll show you with the example in Desmos. Just bear with me.